So the question stands as, it is being given that the earth receives solar radiation at a particular rate. The sun can be taken to be a black body. The angle subtended by the sun at the earth is equal to 0.53 degrees. We need to find out the temperature of the surface of the sun. So let us draw the diagram first. This is the sun. At a very far distance r, we have earth. Now it's been given that the angle subtended by the sun at the earth is equal to 0.53 degrees. This is merging at this point. The angle subtended by the sun at the earth is equal to 0.53 degrees. That is, this angle is equal to 0.53 degrees. Now the diameter of this sun can be taken to be an arc of a circle whose radius is r. Therefore, for this circle, this can be assumed to be a arc of the circle. Since this r is very large, therefore the straight portion can also be taken to be the arc of the circle. Therefore, we write d is equal to r into theta. That is, d upon r is equal to 0.53 into pi by 180. That is equal to 9.25 into 10 raised to minus 3. Therefore, we remember this. Now we know that the rate at which the sun radiates heat is equal to sigma into A into T raised to the power 4. This can be written to be equal to 5.6 into 10 raised to minus 8 into the surface area, that is equal to 4 pi into r square, that is the radius square. Now radius can be written to be equal to diameter upon 2 whole square. This is the rate of at which the sun radiates heat. Now we need to find out, we have been given that the earth receives solar radiation at rate 8.2 joules per centimeter square per minute. Now what happens is that the sun is radiating heat. Now the intensity of this heat at a distance r from the center of the sun, consider a sphere around this of radius r. If we imagine this sphere, then the surface area of this sphere is 4 pi r square. Now whatever energy is being released from the sun is getting distributed evenly throughout this surface area. Therefore the intensity at a distance r can be written to be equal to the heat radiated per unit time upon 4 pi r square. So this becomes as the heat radiated per unit time per unit area, that is the intensity at this point. Therefore we can cancel 4 pi. This becomes equal to, here we have an additional term of T raised to the power 4. Therefore this is sigma. This becomes sigma by 4 into d upon r whole square into T to the power 4. Now we get this as the heat radiated per unit time per unit area at the radius of r where the earth is positioned. Therefore we can equate this to be equal to 8.2 joules per centimeter square minute. Therefore the final answer becomes 5.6 into 10 raised to minus 8 upon 4 into d upon r. We already got the value of d upon r earlier. D upon r was 9.25 into 10 raised to minus 3. Therefore we write it over here, 9.25 into 10 raised to minus 3 whole square into T to the power 4 is equal to 8.2 upon centimeter square has to be converted into meter square into 60, because the minutes has to be converted into seconds. Now from solving this, the value of T comes out to be equal to 5794 Kelvin, that is approximately equal to 5800 Kelvin. So by this method we get the answer for the temperature at the surface of the sun to be equal to 5800 Kelvin.